Okay. Thank you to be here for the lecture of today. I hope that you can hear me. Yeah, let me reconsider the problem which I introduced 2 weeks ago, more or less, in order to restart with the motivation of this last part of of this sessions. Let me say. Let me now switch. Okay. You remember the problem? To park close to the wall. Just really quickly to repeat. About the control loop, I told you a lot. The sense of the control loop. Here we don't have the disturbance in the exam. I didn't put. I will not put the disturbance because I didn't tell you much. But it's an interesting problem in control because typically, I would like to say, one of the motivation, one of the reasons why I need a control is because very often, not only, but very often I have also a disturbance. In particular, if I have a disturbance, this means could be represented by a slope. If I have to park in the slope, it's more difficult because I have this disturbance, which can be seen as a disturbance. And a force here against the motoric force. But the control I need, nevertheless, even without possible disturbance, because the goal, or the goals, if I more than one, let me consider just one. The goal is also a disturbance. You remember this philosophical concept. If in my life I don't have a goal, today I can sleep. Is it a disturbance? No? Also for you to come here, probably. No, but it makes sense. You remember I tried to give you just a feeling, but it's an interesting topic that we have basically exactly the same transfer function between disturbance and output and goal and error. I remember well. This is already something to think. It's not the topic of this course because this is really advanced. You remember sensitivity, the name of this analysis. How sensible is the control loop to these two elements, disturbance and goal. Anyway, I don't want to now to go ahead with this because it's not the topic of the examination, but could be a topic for a bachelor thesis and other advanced, let me say, applications. We don't have the possibility in our time to analyze this. Everything again in linear case. But you remember I told you in dynamical system, the reality is not linear. And then the question is why we are here. Yeah, because nevertheless, in automation, very often Cartesian robots, so we don't, excuse me if I say so, we don't need to be more precise, extremely precise. Did you see Yanis with this soft actuator? It's clear this totally different, or the specification of the challenges, I don't want to say is more or less, but are different with respect to a rigid robot for the production that moved in left or right in the Cartesian form without rotation, we can understand that the challenges of the requirements is more complex. This means in automation, for instance, very often we don't linearize because the system can be considered linear. In Cartesian robot, I don't know if you work with the for instance with the drones, you have rotation, pitch, we can linearize. There are approaches, and we can use exactly this. But with the linearization, we have to be aware that we lose something. Tailor. This is a Taylor. Could be done if we don't need to be extremely precise. Anyway, we have to consider can be applied nevertheless. In automation, I don't want to say that we don't need to be precise, but very often we are close to the linear system. This means we can linearize and we can say, okay, we can prove this work. It works nevertheless in accordance with our specifications. Okay, look, why I am showing you the system here again. Because today we will see how I can design GC of S and why GC of S is there. This structure here isn't a possible controller. It's not the unique one. How many controller I have? Infinite up to infinite. Because a controller is a function. Yeah, it's a function, in a particular function because it's represented in S domain. In S domain. It's comfortable to work here if the system is linear, it's comfortable. Do you remember? Allows also to analyze very well what happens between 0 minus and 0 plus. Do you remember this idea? I sketched that. I don't ask in the exam. But extremely important for us when we have a change, when something changed, to analyze what happened in the system before and after this change. Do you remember this analysis? With S, we can analyze very well what happens before, what happens after, if we have an impulse, if not. I didn't invest much time, but it's enough. If you look again the presentation, I will upload also the material. That is really strong, a really strong tool. Why that? Because we frozen the time. This means we analyze as if in German is als ob. We did a photograph of the phenomenon, or the phenomena, if I'm more than phenomenon, in all horizons. In fact, the Laplace, if you think of the Laplace, is an integral over time for the whole horizon, from 0 to infinite. This means it's as if, of course, this is an emotional explanation, it is a feeling explanation. But it's a possible interpretation because otherwise it's extreme abstract, what in fact we call imaginary domain, imaginary function, complex function. We consist basically in imaginary part because if the imaginary part is 0, we fell down, we end up in a real part, in a real function. Because basically we cannot do a photograph from today until infinite. It's something extremely abstract, but extremely effective. Also to analyze what happens in infinite time, in infinite small interval of time. Look at the slide, or the slide I will upload, and we can really understand a little bit how strong it is. Practically, we have also other advantages. We didn't see any differential equation. For instance, this is also an advantage. Again, in linear case. But also this 0 minus 0 plus is nevertheless is something which we can be used because if I have a change, we have always analyzed if the states before the changes, after the change are continuous. I mean, if the if the change generate not continuous state or not continuous function, this is extremely important for us. If you think about in capacitor, we have seen last time. If the change generate in a step in the voltage of the capacitor, the current is an impulse. We have to know if it's an impulse or not, because an impulse theoretically could generate problem in the system. Impulse mathematically is an infinite amplitude. This is just in a mathematical expression. But you remember I tried to, in the first lecture, to show you what practically an impulse is. Could also destroy the system, no? Because in a small time, large, no, not infinite, but large amplitude. Coming back to this form. This is one of the form of a possible controller. Why I consider it this form? Because in automation, it's very often used. Therefore, we are here to analyze automation. But we have also different, also in S domain, different structure. But this structure here is very used because we will see that with this structure we will end up today. We will see in PID controller, or more general lit-leg, let me say so, controller, which are really in automation very often used. Excuse me. Exactly. Why I am considering this example here? We have in the slide, in my manuscript, also a robot, positioning of a robot, but it's a little bit more complicated. You can see, I will apply nevertheless, but I will not give the robot because the calculation not complicated. We need more time. We need more time to realize the calculations because I can show you why. The procedure is the same. The procedure is the same, but in 20 minutes, half hour is the time you should be dedicated to my part. Probably you don't have time to do all calculations. The concept remains the same. I will show you a robot at the end just to show you that we can do a lot of things now with this. We can apply not only in the car, or I don't know which kind of example I have, but this is something which can help in the exam without spend a lot of time in calculations. Okay, this is just a possibility is applied. Let me see what we have seen until now. The first question was track 1 meter. You remember, track 1 meter means that when I start with the auto parking system, the intelligent part of the car measure with a sensor the distance, and then sets and a suitable distance. I mean, in the example, didactically, assuming that I have a 1 meter, 10 centimeter, the distance. The intelligent system of the car sets as a goal 1 meter, because it is able to consider something more, because I will tell you why that, because nevertheless, for safety reason, in general, we can understand that to be precise is something which happens not in the real cases. This means to track my signal, which is 1 meter, is the first let me say, requirements. With the knowledge which we have in this course, we can track this just asymptotically, because I didn't tell you method in finite time. Do you remember this theorem of the how I call this final value? No, exactly, final value. It seems to be that here I will achieve the goal in infinite time. Is the problem? No, it's not a problem, because basically, practically we don't have a linear system, and the non-linearity due to the static friction allows to say, I told you a little bit in dynamical system, I have to say that somewhere I will stop. Now, it's an approximation what we are doing here. Of course, an approximation. For didactical reasons, I don't have time to introduce in a real. What is the meaning of real? Also, it is real. And a controller which works in finite time. What doesn't control in finite time? The sliding mode control, for instance, could be a method. Introducing the friction. If you remember this concept of switching, the friction is in the switching function, or the static friction better to say. Let me go ahead practically to solve the problem, to, let me say, approximate or to reach 1 meter in infinite time, which is not realistic, but in the real case, it works. This control, it works, because the system consists of an static friction. Somewhere and when let me say, the force which apply to the car does not overcome the static friction, we stop. It's clear. Apply this in the exam, no, concretely in the exam. How to apply this? You can find this theorem again in the data sheet. You don't have to have in mind. This means the transfer function, or the better to say E of S, or if you want, the transfer function between the input signal, which is our goal, the transform in the Laplace, and the error, is this here. This is the transfer function. But if I multiply the transfer function by R of S, the Laplace transform of my goal, which disturbs me, because I have to reach this, is exactly EOS. This part here. Transfer function multiply this. The transfer function, do you remember? 1 divided what I have in the, let me say, between EOS and XOS. This is the goal. No, excuse me. In the loop. We are in the denominator. What we find in the loop. 1, if this is negative, plus this multiply this. In the numerator, we have a 1 because it's what I find directly between this signal and this signal. The input and the output. But if you don't remember, you can find if you don't remember this rule, you can find the data sheet. Theoretically, you should calculate again, but it's not required to calculate the transfer function, because we did didactically in the lecture in order to understand where this transfer function comes from. And then you remember, I gave you this recipe to directly calculate. You don't have to learn anything. Here, I have to tell you a little bit more scientifically. In the exam, look at the data sheet. Because you don't have much data. Now, if you do the calculation, believe me, I don't want to repeat everything. For h equals 0, in this case, because the question is how many integrator I need. The question in the exam is formulated in this form. Calculate the minimum value of h in order to achieve the goal 1 meter. Why the minimum value? It's formulated in this form because an integral, to realize an integral, costs. It costs. Costs because if you do this in analog form with operational amplifier, operational in the continuous form, operation amplifier, excuse me, this cost not only for the component, but cost also to stabilize the system in temperature. Anyway, it's not so, if you can avoid, it's an advantage, practically. Also, if you realize in the microcontroller, in discrete form, I have here a master and an optional course in discrete control. I don't know if you have seen. It's complex, I mean, costly, but not only in terms of calculation law and the controller. If you do the controller in discrete, it's not it's not the topic of this course, but also in terms of dynamics. Is necessary very often in integral. We have seen also in dynamical system, but dynamically, not always, in particular if you have more than one. Yes, is the example. I mean, dynamically could generate some requirements. This means if I can avoid, better. In this case, we can see that I don't need an integral. Why that? Now I tell you something which I already told you a little bit in dynamical system. I don't need, because the system, or at least the system we are considering in the context of the problem, the auto parking, consists in an integral in sense in the sense physically. I mean, if you look at the transfer function, we have an integral in the system. We have an integral in the system. This means that this integral action is still there, is already there. In this sense, I don't need, if I want to track in step. Of course, if I want to realize in cruise control, control of velocity, S is not there. You remember I calculated for you the transfer function for velocity. And we can see that the integral is not there. The reason, you remember I told you between velocity and position is an integral. This means in this case, we will see an exam exercise. We need an integral. This means, please pay attention, the loop at the same transfer function independently if I control position, if I control velocity. Because at least if this is in a step, control of a constant velocity, this means GC must be the same for control position control and velocity control. But this I will come back on this topic later. Now, to introduce the lecture of today, what about Ki? And then it remains just GC to be clarified. Ki is something a little bit in between. Yeah, between again, this I will come back later on this assumption. Recall this assumption. It's not a conservative assumption. Conservative means something that something which limits. It's something in between. Even though the effect is an effect on the transient, it's in between because we analyze approximatively, or we design approximatively Ki, considering nevertheless in a steady state situation, but different. Look here, look at this picture. And now we understand very well why we need a GC of S. Or another part of which belongs to the control. Typically, I would like to achieve 1 meter, in any case, not in infinite time, in a reasonable time. Okay, it seems to me that I put 1 second. I would like to cover 1 meter with 1 second. Why 1? From practical calculation. So in the exam, I will put a good number, no? Because it doesn't make sense to generate problem also in the calculation. Something like that, probably 2 meter in 2 seconds, or 2 meter in 1 second, doesn't change much. Nice number. And the idea is, assuming that, and now the assumption I will clarify, that I am able to answer, or to follow, better to say, this no dashed line, which is our reference, with a steady state error. Now is the point, steady state error, which I can fix 10 up to minus 6 meter. Now we know that I will demonstrate also. I didn't have time to do more precise, but it's clear what I intend. That the answer to the step is not let me say in a line, but it's an exponential function. That we know. Electrotechnique, I told you also. But conceptually, if I consider possible in the analysis, please pay attention, to put in a ramp in input, I can demonstrate now with the calculation, which the system will approximate the ramp asymptotically with the ramp with the Sierra, but in accordance with the system which I have, with a bias. Of course, the real control didn't put a ramp, didn't put a ramp because I have to stop at 1 meter. If I put a ramp, I will stop at 1 meter. Now, question is, in a possible project, could I put a ramp in the early stage of the auto parking phase and then switch in the step? Yeah, this is a project. It's not the case of an examination. But to design KI, think to design just in the offline part. Think about to analyze the system, the answer of the system, if I put in a ramp. Again, could be also considered in a ramp in real case, but just in the early phase of the park phase, of the park process, let's say. But forget this because this is really complex because we have a switching input. No? To analyze, to calculate KI, which somehow approximatively will achieve, why I say approximatively, I will tell you a little bit later again. My goal in 1 second, I test offline my system, which at this moment consists of age equal 0, this means no integrato, and just in KI, which multiply, of course, the transfer function of this. Now, let me analyze what happens if I have a ramp 1 multiply t, why 1? Because this is exactly the velocity, no? It's 1 divided 1. Therefore, I put here 1. If I have here 0,5, I have to put 2. Because it's 1 divided 0,5. Did you agree? No? Twice the velocity. Yes. The slope, no? It's the slope, the velocity. Multiply time is the position. Again, now the problem is as before. To calculate KI, we have to solve the problem which is at the same form as before. But now in input, we have a ramp. Let me see, page number 5. Yes. Look. We have a ramp. This means 1 divided S square is the Laplace transform of the ramp, a unitary ramp. If I have to achieve the goal in 0,5 seconds, I have it 2, because it's in the ramp with a slope equal 2. Now, I see you a little bit perplexed. It's clear, no? I reach 1 meter in 0,5 seconds. Yeah, it's 2, because it's 1 divided 0,5. 0,5 is 1 divided 2. Yeah, it's 2. Sometimes, yeah, it's 2, the factor. But this part here is exactly the same. Please pay attention. Now, age was 0 because we don't need an integrator in the auto parking. I worked with a student of mine in Wolfsburg, in Volkswagen. The name is Philip Huger. If you looked, Hugh Hager, at 100 patents on different topics, but most of them in auto parking system. If you look Google patents, you can find him. The auto parking in the Volkswagen is realized with an adaptive P controller. We don't have an integral because the integrative action is in the system itself. If the goal is to achieve the position. Now, if you do the calculation and as I impose, does this error steady state, assuming that I will achieve somehow the steady state, everything is ideal because I didn't apply really in RAM. I can do that, but I don't do. If I do the calculation, we can see that we have a lower bound for Ki larger than this one. I will follow an ideal ramp. The ideal means which I don't apply, but the system will move as a ramp. if the value is larger than this one. This means exactly what I told you. Yes. Yeah. That somewhen the system will fall over the run. Now, the question is, but somewhen, what is the meaning? The meaning is if I apply really in a ramp, I will overcome, I will cross this my goal. In fact, what happens, what could happen is something like that. I try to, at least in 1 second, I don't know if really I will approximate with this error the ramp, because I didn't apply practically the ramp. But in any case, I will tend to my goal, even though I have a step. I mean, Ki is responsible for the velocity in any case. For the velocity in any case. But really, I apply the step. This means the system will approximate the step, but the risk is with not appropriate Ki, it's not appropriate Ki, that I will overcome this limit. Very important, nevertheless, that I will not overcome 10 centimeter. I mean, you remember I told you the wall, the distance of the wall is 1 meter and 10 centimeter. This means the system will put as goal 1 meter, but should also consider that this oscillation should be not more than 10 centimeter. Let me see if I forgot to say something. And to guarantee this limit related to the overshoot, now we need one possible approach to introduce a correction using GCS, another part of the controller, which correct with, of course, we reduce the velocity. We somehow yeah, we obtain the goal not exactly in 1 second, but again, everything is somehow approximated. But very important that we exceed 1 second in a reasonable time, but more important that we don't crash again the wall, which is not in 1 meter, but 1 meter 10 centimeter. And this means this overshoot must be not more than 10 centimeter. Let me see if I can improve my explanation. Again, it's an approximation because this calculation for Ki works asymptotically. S equals 0 in this context means T infinite theorem, T infinite. This means I don't know where my answer is at 1 second, but increasing Ki, where is Ki? Not here. No, 1 second, I don't see. Therefore, we have a lower bound. Increasing Ki, I will approximate this situation. I will approximate this situation. But of course, the error which I fixed here is achieved at infinite time. But increasing Ki, I will approximate that in 1 second I am basically at my goal, except something larger, infinite small larger than this one. If Ki is infinite large, but if Ki is yet infinite large doesn't make sense, is too large in order to achieve exactly something like that. Again, I will achieve this just in infinite time. It happens something like that when I apply the step. The idea is finally I have to apply the step. Don't care about the fact that I can switch. I can do also this, but this is more complex. What I do with the red line is something which I do, let me say, offline in order to set KI. This is done. This is done that this intelligent part of the controller, which is in the microcontroller of the car. Now, the idea is if I have an error too large, if an error too large, how I can reduce the error or how I can avoid the error to be sure that I don't crash again the wall. The wall is not exactly 1 meter, it's 1 meter and 10 centimeter, but the system sets for safety reason. Typically, I remember the project Volkswagen, something less. But of course, we can also exactly put 1 meter and 10 centimeter and then try to answer to realize an answer of the system without overshoot. We can do that. We can see here the overshoot equals 0. This is the requirement. Okay, this is a little bit the introduction. I need 3 minutes. Yeah, it's the time to call, and then I will come back and we go ahead with the presentation in order to understand how I can maintaining the KI, which guarantees nevertheless my speed, exactly guarantees not because the GS will reduce the speed, but we reduce the speed in accordance to our specification. Nevertheless, in a reasonable speed of parking, and reduce it or eliminate, let me say, the overshoot. The risk is if one is exactly my wall is not the case. In this case, I will crash out again the wall infinite time, at least mathematically. If the wall is 1 meter and 10 centimeter, we can see that I will crash once, for instance. Could be also more than one each time that each I exceed 1 meter and 10 centimeter. Okay, let me give me 5 minutes and then I come back with the presentation. Okay, as I told you, just in time. Now we will see that using this GCOS, the rest of the part, the rest part of the controller, GC is just a part, I can correct possible error, possible overshoot, which really could be dangerous. Could be dangerous. You have to guarantee that I don't crash, or at least I respect, in general, the requirement, or at least I can respect the tolerance, which guarantees that we have a given precision related to my goal. It's in a positioning. Today is in a positioning problem, displacement problem, better to say. Look, do you remember I told you that for each we can see here, for each transfer function in the loop, y divided r of s, y divided d of s, es divided r of s, we have the same denominator. I told you about that a lot. That is many consideration I did. Let me analyze the denominator. In particular, for us, it's interesting, basically, where is this transfer function here? But again, in terms of denominator, they are the same. We are considering the first one because the output is the position. I mean, I must guarantee the stability. This means not infinite, let me say, position. Unstable means we analyze the instability or stability aspects in the dynamical system. I mean, when I have to achieve a finite value. Moreover, the idea is to achieve the final value. And this we have seen that it seems to be possible, but with an overshoot not more than 10 centimeter. But in any case, in terms of denominator, for all transfer function, we have the same denominator. Look, what we learned in high school or in elementary school, that the denominator must be not zero. This means the critical situation is when the denominator is equal to zero without just a feeling. And zero, we learned that we cannot divide by zero. In terms of control system, in terms of my calculation, what is the meaning of this? As I told you, this expression here is a complex function because it consists of a function in S, which is a complex variable. This equality means, I don't know if you remember in Math 1 or Math 2, that I have to split, if I consider the problem a little bit more in depth, this condition here in two conditions, one in amplitude and one in phase. I mean, a complex equation can be expressed in two, let me say, real expression, one in amplitude and one in phase. I don't know if you remember. And a complex, just to recall a little bit, Math 1 or electrotechnics, a complex value. Yeah, we don't have we have a complex value, but in terms of, we have a complex value, but in terms of complex functions, the concept is the same. How I can characterize a complex value? Amplitude, in German, Beitrag, and phase. You remember this? It's the same. This constraint equals zero can be characterized really means concretely. What do I say concretely? Because here is quite abstract. When this happens, in more real sense, because you don't ever forget that this imaginary analysis, this complex analysis, reflects the reality because we started from the physical system. There is somewhere to come back to the physical system. Now, when this is zero if the magnitude of this product is one. Why that? Because this function here, or this expression can be written GR of S multiplied GS of S equals -1, right? Equal -1. It's the same. This expression can be written GR of S multiplied GS of S equal -1. Now, this expression is equivalent to say GR of S multiplied GS of S equals -1. This means, think about the GR of S multiplied GS of S is a complex function. If you, of course, complex function is a little bit abstract, but at the end, the complex function in output at complex values. When a complex value is equal -1, when the amplitude, Beitrag in German, equal 1, and the phase -180. I don't know if this is clear. Because we have a vector oriented on the x-axis, or the real axis, but in negative form. This means you have two conditions, must be satisfied, two conditions. It is clear that these two conditions satisfied GR multiplied GS equal -1, because we have values with amplitude 1 but oriented on the real axis negative. This means the phase of the negative real axis is minus pi, minus 180. I don't know if this is clear. Both I need. Because I have an amplitude in my, I don't know if it's unclear, these two conditions. These two conditions are real conditions which states this complex condition. If you think about, here we have a complex value. The complex number, let me say number, equals minus 1. 1 in the complex number is equal minus 1. If the amplitude is equal 1 and the phase 180. I show you probably, if this is difficult, I'll show you what I intend graphically. All point here are characterized by an amplitude 1. This is 1, this is minus 1, this is j, this is minus j. Did you agree? No? But it's not enough to say that all these values are equals minus 1. I mean, I am looking for this vector, or this complex value. But this complex value is characterized by amplitude 1 and phase minus 180. And this must be valid for each S. For each. This is the condition. Let me go ahead. Seems to be complex, but it's even though we are doing a complex value. This means we already characterized mathematically the critical situation. Then I will tell you a little bit more in depth about the denominator, because the denominator states the position of the poles. We say the poles in the nomenclature of the transfer function. And we can understand, if you think about, I told you when I introduced the Laplace transformation, I told you that if you have a poles with real part positive, we have an unstable, or at that time I didn't tell you about the instability, but having a function, the Beck transformation is in a function in time, which is going to infinite. Do you remember I told you when I introduced the Laplace transform of an exponential function, if the exponent is positive, I have a transfer function with a pole with real part positive. And we can, in this sense, guess the stability in terms of S is guaranteed if all poles have a real part negative. Do you remember I told you introducing the Laplace transform? I will come back a little bit, let me say a little bit later about that. But I told you that when I introduce exactly the concept of the Laplace transform of the exponential function, I didn't insist on this because I know that in Math 1 somebody told you about that transfer function was also a little bit done in electrotechnic. But anyway, in accordance with what I already told you in the context of the transfer function, at the Beck transfer function, if you remember, the Laplace transform of the exponential function up to at is 1 minus, is 1 divided, excuse me, s plus a, no, or the alpha, if alpha t. Now, if alpha is positive, we have a function, excuse me, 1 divided s minus alpha, if you look in the table. S minus alpha. Exponential function of alpha t is 1 divided S minus alpha. Now, if alpha is positive, we have a function which is going to infinite. Let me say in a system, or an answer of the system, or on a function which is going to infinite for a system means that the system is unstable. If you consider the answer of the system as an exponential function with a positive exponent. This means the poles, if alpha is positive, S minus alpha means S equal alpha, is alpha positive. This means the real part is positive. We can characterize the stability of a system in our case, because we are speaking about the system, through the position of the poles. I told you a little bit, now I will repeat, but I know that you know, I will come back a little bit later on this. But assuming that this hypothesis guarantees, we already assumed when we calculate the limit for S equals 0, which is equivalent to limit to t infinite, we assumed that the limit exists, it is finite. Let me go ahead. Nevertheless, here we have something more, I would like to say. We have two conditions, two real conditions, please pay attention. And complex condition is transformed into real condition, which say when we are in a critical situation. This situation must be avoided, definitively. Yeah. Now I will introduce the Bode stability criterion, which is basically isn't a theorem, or better to say, this criterion is stated by the Bode theorem, or one of the Bode theorems. And the Bode theorem answers the following question. Is the closed loop stable? So basically, more in general, I wrote here the relative stability. Because I would like to be more precise now. Starting from the open loop system, the open loop system is this here, GR multiplied GS. Starting from, basically, starting, let me say, from GR multiplied GS. If you remember, I called this L0, something like that. That's the open loop. The open loop means if I open the loop, consider D equals 0, I have basically this product between R and Y of S. Y of S is equal this multiplied this, GR multiplied GS multiplied RS. Therefore, the open loop is the product of this. Why provide a relative stability criteria? Because starting from the open loop, we can analyze if the closed loop is stable or not stable, but somehow states how stable it is. It's a little bit strange, because stability is in the system is stable or not stable. But for us, for our original problem, which we want to in any case have a system which is not diverge, but we want a system that is does not exceed much, let me say so, practically my goal. And in this sense, we will see that the criteria of Bode states the measurements, I would like to say, of the stability, because of course, the system here is stable in the strictly, if I consider strictly the definition, but it's more stable, this one, than this one. Let me say in this sense, because the overshoot here, it seems to be, at least graphically, larger than here. Therefore, here I spoke about if in the relative sense. Let me I wrote here, one second. Ah, no. And this is extremely important because allows really um, to apply practically. This is a question, but the question related to the stability, both say something more. But of course, answer also this. No? Yeah, this is the sentence which summarizes what I told you about the position of the poles. That is the roots of the denominator, no? Which corresponds, do you remember at the eigenvalues of the system, if the system is observable and controllable. About that, forget, because I didn't tell you much about observability and controllability. But if you go ahead with my fields in control, you will realize this. Now, okay, now exactly. The open loop, as I told you before, the open loop transfer function is GR multiply GS in S. Give me 10 minutes, and then we will take a rest. No? So we conclude this theoretical part, and the second part we apply. Now, as I told you, we have two conditions. Please pay attention, two real conditions to be satisfied. And the complex condition is transformed in a real case in two conditions, two real conditions. This means, if you look at this slide, that we can define an omega c, the name is critical frequency, in which, for which we have the phase of the open loop equals minus 180. It's exactly what I look, because my open loop transfer function. Why open loop? Now, because I managed to open the loop. I mean, for the closed loop with ds equals 0, this is the transfer function. For the closed loop. If I open the loop, the transfer function between, let me say, Rs and Ys is exactly this. Gr multiply Gs. Now, for Gr multiply Gs in S, not in amplitude, we can define a critical frequency when, or at this critical frequency, we have the phase minus 180. This means I wonder if exists a critical frequency for Gs multiply Gs in which we have a minus 180. Please pay attention now. I didn't introduce the theorem, but we are speaking about omega and not S. Because the theorem, the Bode theorem, I'm not introduced yet, but it's a really strong tool because not only allows to evaluate the relative stability, also the stability of the system, starting from the open loop, transfer function, but considering just the steady state analysis. This means I assume that I will have a steady state, stable structure, and then we will see the relative stability. This means I assume that the denominator are poles with real part negative. And I can ask me about another interesting frequency, which is the crossover frequency, in which we will call omega g in some literature, in which the amplitude is equal 1, in order to analyze these critical conditions. Okay, look at this picture. This picture clarifies everything. Look, we have here a crossover, no? We call here crossover frequency, omega g. And it seems here, in this case, we have two if this is the Bode diagram, this is the abstract Bode diagram, very often we have just one omega c, but it could be that you have also more than one. In this course, we will analyze the theorem just in case of one crossover, but it could be also the omega g could be also more than one. In this course, in this hour which I have at disposition, we will consider more standard, which is covered most of the cases. Of course, if you have a multiple omega g, a multiple omega c, as in this case, we have another version of the theorem. And then we will apply in the second part of the lecture. Basically, the theorem, which is a stability criterion, of course, more than a stability criterion is a stability criterion. It's a relative stability criterion, but also it's a stability criterion. It's, I copy from a book. Look, the part in red. Considering an open loop transfer function, this means the product between the transfer function of the controller, which is not completed yet, because I have to calculate GS of S. Thanks to this result, multiply the transfer function of the system. This is the open loop transfer function, this here. Open loop transfer function. Strictly proper means that I have more poles than zeros. Of course, you see, this hypothesis is not guaranteed. We have to put some conditions. I don't have time to extend this Bode diagram in this case here, but this covers also most of the cases. No poles located on or on the right imaginary axis. This means not unstable system, as I told you exactly at the beginning, or on the axis. But on the axis could be possible, but single pole. This means just one. Just one. Of course, if I have more than one, for instance, if I need two integrators, we have other version of this theorem here, but remains on this because this is nevertheless much. What just one? If I have more than one, if I need two integrals, I have another version. I can consider a different as an extended with some condition extended theorem. Again, just only single critical frequency, I told you, and only one cross over frequency, a standard situation which covers many. If no, of course, I have to consider an extension of it with some conditions. Look, finally, the closed loop system is asymptotically stable if and only if, excuse me, norm is an if, no? It's not an if and only if I made mistakes. If norm of GOL less than 1, or dually, we can consider that the phase at the crossover frequency is minus -180. Yeah, excuse me, it's an if and only if. And I remember because look, otherwise it's unstable. This means as if and only. Therefore, I told you as if and only if. I correct me, but wrongly. Otherwise it's unstable. But the strongness of this result is starting from an open loop transfer function. Starting from an open loop transfer function, I will conclude on a closed loop transfer function, assuming what is written here. If the assumptions are not guaranteed, we have extensions. I don't have time to tell you, but this assumption is not so restrictive. Believe me, more of the majority of the practical cases, in particular in automation. I will show you some examples. Now, I would like to stop here just with this slide here, because after that we have the case. look, in the second part of the lecture, we will see that this kind of possible let me say controller can guarantee the specification, is in particular in our case. In our case, we will see an elite structure, which is here. An elite structure guarantees that we can obtain the required overshoot. The lag, if I use also the lag, but typically is the lead. I have time just to analyze the lead, but I will show you also the lag. Basically, the lead try to break the system, to slow down the system. The lag try to accelerate. Typically, the application we applied lead because with Ki, or that K here, Ki is included here because this is in a general approach. This K is our Ki, but we analyzed also the Ki already in the first part of the lecture, in which we state, let me say, the velocity. This means 1 plus Ts divided 1 plus, excuse me, T multiply S, 1 divided 1 plus T divided lambda multiply S is the transfer function of the GC of S without K. We will consider later. I need just, we can see here, in fact, I need just to introduce this heuristic approximation to explain how we can complete our exercise or our project. Determine this basically consists of calculated tau, or the T in this literature, T or tau, and lambda, in order to break, in order to slow down the system to avoid, let me let me show you what. Totally their overshoot, if this is required. Of course, it's a relatively strong action, or to limit. If you consider this blue line, which is obtained, considering is enough large Ki, with respect to this one here, this blue line, basically we have an action, a break action here with respect to here. Of course, we pay price, because we are here basically, we slow down let me say, the answer of the system. Okay, I would like to stop here. In the second part, we will complete the design of GC. We do some consideration exactly in the context of exercise for the exam. The exercise could be a displacement problem in automation. Now I consider in a car, but in automation. And then we will see that if I put in the exam the velocity control, could be also in automation important, not necessarily in control, in cruise control and so on. The analysis almost the same. I would like to say the same. This means we can see that in our frame, not only is it irrelevant which system I consider, because when you have a transfer function, I forgot basically where the transfer function comes from. I can neglect the physical system. But also in the control, we can use, let me say, at the end, the same, or some parts which are exactly the same for displacement control and velocity control, or we say in our nomenclature, cruise control. We take a rest. We will come back here in 50 minutes, no, more or less. and then we will complete the exam or the example for the examination in discussing this analysis or design of GC of S, and then we do another exercise, no, completely. So you see, then we have a time really to go in depth also next week and then in February when we met. Okay, let me stop here and then we will start. See you in 15 minutes, yeah, more or less. Okay, we will start just thinking that the Bode theorem of this method covers most of the most of the important application, at least in automation, in which the system, I would like to say, the systems are a little bit easier. Allow me to say, we will see at the end of the course. I will sketch out methods in which we can remove or we can consider more than one critical frequency, more than one crossover frequency, and also more than one poles, and also systems which are unstable. But anyway, I don't include this part in the exam because we don't have time. These systems are complex. But I would like to sketch some methods, exist some method which we can consider, we can extend, let me say, the Bode theorem also for systems which does not respect all hypotheses which I am considering now. But believe me, in particular in automation, but also more in general, most of the systems guarantees this hypothesis. In particular, as I told you, the number of poles in zero. We try to avoid it because they cost from the application. This means we can understand that the hypotheses are not so restrictive and not so conservative. But of course, it could happen in particular systems that some hypotheses are not guaranteed. We have other methods. I will sketch out just for curiosity at the end of the course if we have time, but I think so. As I would like to tell you about a little bit the linearization, because again, this method works if the system and the controller, this means the control loop, is linear. This means if it's not, we can use a different method. One of them I presented in the dynamical system, or we linearize the system. But anyway, we have to be careful in the linearization because it's nevertheless an approximation. Okay, let me conclude this method with the practical application, and we will see the example of the parking, which is a classical example which can appear also in the examination. Now, here is the structure of two possible controllers. We will consider in this course just the lead because it's more views in the sets. Typically, we give energy to the system with a larger KI, which guarantees to speed up the system. Then we break a little bit, we slow down a little bit if necessary. This means in the exam and also today, we will consider this system here as a controller, as GC, the part of the controller. But we will realize that to design this as a dual, let me say, it's a dual analysis, we can see that basically it's the inversion of this, exactly the inversion. What is here the numerator becomes the denominator, what is here the denominator becomes the numerator here. We will consider this once we are able to analyze this. If we need to speed up the system instead of slow down, we will use this one. But this is not typical because it's more practical to break instead of accelerate, let me see. Look, this part, I hope to be more precise if I have a little bit more time at the end. we can see in the middle, at most at the end of the slide, um, approximating, let me say, equation. Let me consider for the lead just these two elements, even though this is also valid for the lag. What about this for approximating, let me say, yeah, condition, or the equation is not correct, but relations. Look at this. This expression is easy to interpret because says that the maximal value, MR, now I have a picture for you, is circa, if I have time, I will show you how we can, let me say, demonstrate this. 1 plus the overshoot, consider in percentage. Let me show you what I intend. Look this picture here. Here is exactly one. We don't need to consider the analysis in percentage, no? But if it's not one, I have to normalize. The percentual is normalization. I mean, the maximal value, this value here, is basically 1 plus S hat. S hat is, of course, in percentual. How can be exceed? Our example was the wall is 1 meter 10 centimeter. This means this maximal value, this overshoot should be 10%. 10%. This means MR is 1,1. In accordance what I am considering. Here the percentual is exactly the value, no? But of course here S is, let me say, is 0, because I don't S hat is defined in terms of let me say, positive. No, if negative, I consider 0. We cannot say negative. This is typical analysis. Should be positive or 0. Positive. If we are 0, this means we'll never cross the maximum. Why we are considering not negative? Because this analysis is asymptotical, no? Somewhere, no? Basically, no overshoot S hat 0. Let me see if I can. Very important in percent. I mean, if this is 2, this must be considered. If the maximal is 2, is again 1, because now we will use this expression in this heuristic formula, which I would like to a little bit to clarify a little bit, but to analyze or to consider this expression here, I needed to tell you about complex things. Basically, the complex thing is that this is in a relation. This is in a relation between an answer in time, MR in time, and something which belongs to the analysis in frequency, the phase margin. This is the phase margin. It's something which belongs to the frequency. I will clarify a little bit more today, and then we will see next week to justify better, but I need a little bit of theory to justify it, to justify more in depth. In any case, for the exam, it is enough to recall this part here. Yeah, to recall this part here. And you can find also this approximating equation in the data sheet. Let me see if I forgot to say something. I don't think so, because it's zero if you don't have overshoot, because as if I will consider the steady state analysis, basically will be zero at infinite time. This means no overshoot. S hat zero, no overshoot. Because we don't know when the overshoot happens. Therefore, we don't consider negative part. I mean, we don't have a time to be considered. Let me see if I. Yeah, if I write, for instance, 0,1, if I write here 0,1, in this context here, in this context, means that I exceed my goal, which is normalized to 1. I exceed of 10%, of 10%, 0,1. This is the goal. Not necessarily 1. In this case, it's 1, because I consider 1 meter. Because I'm considering 1 meter. But if this is 2 meters, and I want to exceed just 10%, I have to write nevertheless 0,1. 10% of 2 meters is 20 centimeters, yeah? Right. I will consider always 1. Because it's my goal. My goal is 1 in terms of normalize. I would like to say normalize. At the end, I will have nevertheless 1,1. This means to exceed, or the overshoot, equals 10% of the final value. 1 is the normalized final value. Let me see if I can clarify it better, but I think this is a little bit already. Again, if I have 1,1, this means 10% of the final value. Yeah, this is a little bit more complex. I will show you a little. I will bring you some consideration later, but you don't need for the exam. But I would like to explain. This we can understand. No, I can consider the maximal peak. Yeah, or no, the maximal peak as the sum of my goal could be. It doesn't matter what, which I normalize it to 1 plus S hat in percentage of the maximal goal. 10%, and then I can interpret it, how much if I read the real value. Here's a little bit more complex to justify, but I will bring you a little bit some equations in order to understand why it's more complex. It's more complex because it's in a connection between answering time. You can see this R came from the answering time, and a parameter, this phase margin, which I will define in a few minutes, which is in a parameter which is not in time, but is in frequency. This means steady state. This means it's in a connection between time and frequency, but also in the meantime, transient and steady state. Very important. Time and frequency, connect time and frequency, but in the meantime, transient and steady state. This means we can understand that this is not immediate yeah. To explain this, I need a little bit to show you some mathematical aspects, but believe me, we need that because we need to transfer specification in time, which is our goal, and specification in frequency in order to use the Bode diagram. This is the goal, but to justify this approximating this approximating relation, I need to introduce some mathematical aspect. I don't want to do now. I would like to do more concretely the examples. Let me conclude with the method coming back to the presentation. How I do? I have to introduce the phase margin because I forgot to do. The phase margin is the difference about the phase margin. I already somehow told you. Is the distance, I mean, to calculate the phase margin, I have to calculate the crossover frequency, omega g, in accordance with our notation, which basically, as I told you, and when the amplitude of the open loop transfer function equal 1, this means in here must be 1, or if you consider in decibel 0, logarithm of 1 is 0. Yeah, I put the just I sketch g of omega L j omega, but of course to be precise, I have to consider the magnitude. Let me correct. It's the magnitude, the Bode diagram. Let me. Where is now? Yeah, here. Yeah. Here I put exactly the phase. Here I forgot. Then we can see I defined implicitly the phase margin, which is the difference between our critical frequency, phase, our critical phase, which is 108, better to say minus 180, and the difference between minus 180. Let me to be precise, and the phase at omega g of my open loop transfer function. Is this difference? Why this is a phase margin? Because it's the margin which I have with respect to the critical situation. You remember the critical situation is amplitude is equal 1. Here should be 1. I have to write 1. Or if I write, in this case, I have to write 1. When this happens at omega g, I should avoid minus 180. Do you remember the critical situation is amplitude 1 and you remember and phase minus 180. This is still asymptotically stable in accordance with the Bode theorem. I showed you a little bit in the presentation. This is the phase match. I show you again this concept here, and then a few minutes we will conclude. It's really easy. You remember this was the discussion that this complex expression can be equivalently written more concretely in two real conditions, this here and this here. Now the question is, when happens both together? Is the question. When happens both together, we have the critical situation that we have a 0 in the denominator. And then to do that, do you remember this analysis omega g and the phase omega g, and exactly this. At omega g, this means when, what is omega g? When the amplitude is 1. Or in decibel, when the amplitude is 0, logarithm of 1. We need that the phase margin is positive. This means I have to be, let me say, in the upper part, of the phase margin. I have to be not less than 180, minus 180 degrees. It's written here. This is a little bit the sense. More practical is more practical interpretation, but really, really practical, intuitive. What is the meaning here of this two of the, excuse me, of the condition of both? We use this dual condition. Can be used also this direct condition, but basically very often we use just this one. The practical meaning is that if I come back here, a signal, let me say, somehow, let me use the word somehow negative, I sum up here. This is a very, very rough interpretation, but intuitively we can understand that we have a plus minus. If the signal which we come back here is negative under some conditions, no? Because it's not enough negative, but intuitively is this the idea? Of course, I will increase the signal here, and if this persists, this is the sense of with some conditions, I will generate a system which will be unstable. Let me see if I can improve this. This is really intuitive. Because of course, for a short time, it could be also this signal negative. Therefore, the analysis steady state, if this persists, and this is something which can be interpreted in this, let me say, steady state analysis, which came from the S, or the Laplace transform, which freezes the time. Let me say, something more, but anyway, it's intuitive. This means it's not so precise, but intuitively we can understand this sense here. If persist, therefore steady state analysis, a signal which is negative, I will increase here the error. Okay, we come back on this possible interpretation next week in order to go in depth. Let me concretely show you what we can do with this equation, which I today interpreted roughly. Next week I will go more in depth, but of course I don't want to put or to be boring with many mathematical aspects. Look at this. When I have MR, I have the phase. The phase is given radians with this empirical equation. Let me see. Exactly. It's given radiant. It must be said this. Look, using this table now, I have the phase margin, which must be guaranteed, or better to say, what I request. Again, let me show you again. You have the specification in terms of S hat. Where is it? Yeah. This here in rad, what I need, for instance, here it seems to be that I don't want oscillations because the S hat is 0. This means MR is 1. 1 is our goal. Normalize, of course. In our case, normalization is exactly 1. In radians, I will transform in grads. This means this is what I need in terms of phase of the system to obtain an answer without overshoot. Now, using this table here, what is this table? MATLAB can work more precisely. Let me show you the sense of these two tables, which is better to look later here. Or probably at the beginning to clarify, I can show you exactly here. In our case, k is equal 1. What is this curve here? Is basically the phase of this transfer function, which is the transfer function of the controller, parameterized by different lambda. Here, k equal 1 does not change the phase because, as I told you, the phase, the phase of the constant, it doesn't matter one or another number is always the same, no? Because the phase of a constant positive is 0. It's basically the analysis of this, the graph, analysis into the graph of this function here over calculating omega t. Basically, the variable here is omega t. Put here S equal omega, steady state. Maren clarified in the electrotechnique, S equal omega means the real part of the exponential function of the, you remember, I told you a little bit also in my lecture when I repeated a little bit the Laplace transform. Means steady state because the exponential part of the answer is not considered equal 1, basically at the end of the transit. Basically, as a function of omega t can be graph, the computer realized the graph, the computer we can realize is much better than the resolution is the resolution of the computer. Here we can see that I put a different phase. This is the phase of this function here for different lambda as a function of omega t. Now, in our case, it seems that I need to achieve the goal without, the goal is no oscillations. The phase margin equal 60. This means I consider here in the line 60. I will, for instance, take lambda equal, I don't know what is the, is between 12,5 and 16. I will consider the maximum point. Of course, I can consider also lambda equal 20. I can consider also lambda equal 12,5 and reading when this happens. No? We can consider more than one solution. No? We have this one. We have this one. But why we take the maximum? Because we want to minimize the sensitivity of the system. I mean, in the maximum, let me say, independently of what independently, I mean, we have in a large interval in which the phase does not change much. This means it's not sensible to approximation to, I mean, it works for a range of frequency. If you consider the line here, and you consider, for instance, this point here, which corresponds to omega t equals, here it's difficult to read probably. I will print this in the exam. It's better to look here a little bit. We can see that for a small range of frequency, we have a big variation of the specification. This means typically we consider the maximum. When we have in the maximum our value of omega t, or omega tau in some notation, to calculate tau or t is easy because we have the value. It is enough to divide it by omega g because the specification must be guaranteed at omega g to have the guarantees over time. This is again the concept which I told you again today in the morning, because in the complex analysis, we frozen the time. Of course, the assumption is the system must be stable. This means should be the steady state achievable. This means the poles must be all with real part negative. And just single pole in the imaginary axis, because otherwise the system is unstable. I don't know if you remember a little bit in math, but you don't need now for in this short time to go in depth. I mean, the Laplace transform of 1 divided s squared, we have 2 poles in 0. It's in a ramp. We have seen also today. The system is, the signal is infinite. If this is the system is unstable with 2 poles. The system must be in this approach, with this analysis, both at least stable. At least stable. Okay, let me do now the calculation for you extremely, and then we can see again the application here. No? Let me switch on the lateral camera. Now, yeah, assuming that S hat equals 0, I apply this equation here, which I will clarify a little bit better next week. The phase margin which I need is 10,4 radians. I transform radian in degrees because the table which I will give you is in radians. This is what I need. Now, I need to calculate omega g, and at omega g, the phase of the open loops transfer function. Look, it's not extremely difficult. Again, both is there just to interpret what we are doing. It's based on both, but you don't need to do in the example. If you do, I am happy because you showed me that you understood the idea. I have to calculate this omega g with this condition. This is the definition. I will put also in the data sheet this. But how I can do that? What is GOL J omega? GOL J omega, in accordance with the definition, is GR, controller, multiply GS system. But steady state, calculated J omega. You remember, this was 25 multiplied 10 up to 6 was KI. This was S from the system, not from the controller. And this was the poles from the system. Basically, our controller at this stage is Ki multiply GS. It is one calculated at omega g, at omega, excuse me. Amplitude of this. Did you agree with this one? Because the amplitude of the numerator is the numerator itself, because it's real. The amplitude of the denominator, again, the amplitude of the numerator divided the denominator is the amplitude of the numerator divided the denominator. Yeah, I mean, the amplitude of a ratio is the amplitude of the numerator divided the amplitude of the denominator. Here, we have a product between J omega and what is inside the parentheses. And again, the amplitude of J omega multiplied what is here is the amplitude of J omega with this omega. Why that? Because it's root of real part, which is 0 squared, plus imaginary part, which is omega squared, and square, I will cancel with the root. And then I have to calculate the product with the amplitude of this expression here, which is root of what? Real part square, excuse me here, 25 square, plus imaginary part square, which is 10 up to 6 multiply omega squared. Now, I need to calculate omega g. This means I need to calculate this. Now, if you have a calculator, you can use. You can, otherwise, I have to do these calculations. They are not difficult. But anyway, sometimes we need the time. If you have a calculator, you can calculate, you can put this equation in the calculator, you can obtain omega g directly. Otherwise, look, You have to multiply this one. You have to algebraically to do some calculation. And of course, this could be solved more precisely. I don't know if you remember, to consider omega g squared equals omega g tilde. Then we have a polynomial. How possible to say? We reduce the degree of the polynomial. I don't know if it's clear. If omega g squared equal omega g tilde, we have here omega g tilde squared, and this does not change. Pico formula, we obtain omega g, and then we do the root. Gymnasium. We should do so? Okay, if you want. Again, we are not here for math. If you have the calculator, you can solve directly here. You can write this calculator, calculate directly omega g. MATLAB, or I think this normal calculator is able to do that. In the exam, Baru? Okay. If it's not the case, you can solve as I told you, but I don't want to do, because we are not here for the calculation, of course. Look what I'm writing here. Assuming that omega g is clear, we approximate this, is large enough. Nevertheless, it's an hypothesis not so restrictive, because for Ki, please pay attention, for Ki very large, the body diagram go up. I mean, you remember the idea is to design a Ki very large. This means the body diagram is, let me say, is roughly speaking, it's quite high. This means to say that omega g, this crossover frequency, is large enough, or mathematically large enough means that this part here dominates with respect to this one. We can see that 10 up to 6, omega g up to 4. The idea is to mathematically means I don't consider this one. I mean, with this omega g squared equals omega g tilde is clear what I will do. We did in gymnasium. We have 4 solutions. How we can calculate? We reduce this equation here with order 4 in order 2. It is possible because we can see that it's an even polynomial. I come back, it's in a polynomial second order. I have 2 solutions, and then I have to calculate the root of these 2 solutions. Assuming that they are real, I will consider just this real, I will obtain the exact solution. Should be done in this form? No. In the exam, I am not here for math. This hypothesis that is large enough to neglect this is not so restrictive in our case. Why that? Because our idea was to consider Ki very, very large. If you remember my analysis in the body diagram, Ki very large means that this body diagram is in very high position. This means omega g we can consider relatively large. Mathematically, more correctly, I have to neglect this. Look, I have to neglect this. But it's not so difficult to justify this. Why that? First of all, we have this 10 up to 6. 10 up to 6 is 1 million. 10 up to 6 is 1 million, right? I am not in good math. Therefore, I don't pretend that you are better than me, even though this is easy to do something better than me. But this 10 up to 6 came from this Ki. This K up to 6 came from this Ki. Do you remember? This means, look, structurally, this omega g, this component is already large. But of course, this is not enough. We have to say that omega g up to 4 multiplied 10 up to 6 is much larger than this one. But you can see that it's not so restrictive, this hypothesis. Because already for omega g, I don't know, we have to look when this hypothesis, a posteriori, we have to look when this hypothesis is guaranteed. But we assume For instance, for omega g equal 1, we have a 10 up to 6, and we have to compare with 25 up to 2, of course. In engineer fields, when something 10 times larger than the rest, we can neglect. This means this equation here, assuming that is this one. This can be solved in 1 second. You cannot use the calculator. Okay, learn this. We don't need the calculator. But the problem is here, this is not so easy without a calculator. I have to speak with Andreas.
Also ich meine mit dem Taschenrechner.
Ja, Taschenrechner.
Es geht nur
Okay, die
dass du nicht in der Formel jetzt irgendwo die Variablen hast und dann sagst, stell mir das um und solve das.
Okay, it's not possible by Andreas. Andreas don't want.
Doch Andreas möchte, also ist erlaubt ein Taschenrechner, aber der Taschenrechner darf nicht eine Formel bekommen mit x.
Okay,
soll
okay.
nach x.
Okay, this means please use this approximation, which is nevertheless, in our case, valid because Ki is so large that look, this came from Ki. Do you remember Ki larger than 25, 10 up to 6? Because this approach is to accelerate and then to break with GS. This means we can assume that omega g is large enough such that this is negligible. If this is negligible, we have this equation. This remain, and then here we can solve. No? I mean, from here to here is clear. From here to here is clear. I cancel here 2, I have here 2, and I have here 3, right? Always positive because I need omega positive. Omega is positive as a definition. Because otherwise I cannot, the negative frequency for us, no meaning. And then from here it's clear that it's 185. At this omega, we have 185. If you look at this expression, this element here is 185. Should I write? Because it's exactly the case. Minus. No? Is exactly what I have. Now to conclude, this is exactly what I have, but I need 60-degree margin. If you consider this, let me see the rest, 8. Calculate omega g, I have it. I did. This is exactly. No, I second that because I'm confused now. Let me see again what we did. This is exactly what I have, right? No, excuse me. I made a mistake. This is omega g. Excuse me. Too fast. this is the frequency, excuse me. It's not the margin, excuse me for the, let me leave open. It's not the phase margin, excuse me. I am going too fast. This is the frequency. It's here, no? It's this, excuse me for the, yeah. Radians. Again, excuse me for the, it's clear, it is written, it is written. Radian per second, that's like here, it's the frequency, or pulsation. Excuse me for that. Yeah, it is written, also omega g is not yet the phase, but I will show you immediately. This phase is not yet this. It's not yet. How I can calculate? Arctangent of what? Of g omega L calculated g omega. I will consider again as before the g o L, which is this one, divided this one, calculated now at g omega, phase of the numerators minus phase of the denominator. If you do the calculation, the phase of this independently, excuse me, the phase of this independent of this is minus 90 degrees, because it's the phase of j, is the phase of 1 divided j. The phase of 1 divided j is minus 90 degrees. I don't know if you remember in the calculation of complex value. Minus arctangent of the phase of this. What is the phase of this? Is the imaginary part, I mean, arctangent of the imaginary part divided the real part. Now I am asking you, in your calculator, it is possible to do arctangent, yeah? But you will realize that this is almost 90. This means we are almost minus 180. This means now I will do precisely. This, I don't need to put another circa. This means the margin is almost zero. The margin is almost zero. Then it's written here, the margin is almost zero. But it's almost zero, as I told you at the beginning, is enough that I pull up my phase here, as I anticipate before, of 60 degrees. I don't know if it's more visible here. 60 degrees means 14. If I consider the maximum at 14, I will consider the maximum because I want to realize the controller not so sensible to the variation in frequency, because you have many approximation. This means should be valid for a large or larger interval of omega, or better to say omega t. Then if I read here 14, and I go down, I have omega t, or the omega tau, equals 1, 2, 3, 4. Let me see. Yeah. If I have to pull up the phase at omega g equal 185 of 60 degrees, I can read from the table which analyzes or we graph the controller with respect to omega t or omega tau for each lambda. In the maximum, I am reading 14. And in the corresponding, let me say, x-axis, I am reading omega g multiplied t, which must be calculated, or the tau, equal 4, as I told you. This means tau of t is 4 divided omega g. Ready. At the end, the controller is ki, which multiply, do you remember, 1 plus omega t, or in S, t multiply S, omega multiply t, or the t multiply omega becomes in S, t multiply S. And here we have 1 plus, if you look at the definition, I will put the definition in the data sheet. T or tau divided lambda multiply S. Because in the original form and steady state, we have omega instead of S. But look now what happened. This is exactly controller, exact, with the approximation which I told you. Look here what happens. If I want approximate, or the question is, could I approximate the controller? Yeah, eventually. What I can neglect here for low frequency, this is the element which could be neglected because it's divided by 4. I mean, with respect to 1, I can consider for small frequency to neglect this. And the controller becomes this. Oh, what is this controller? I don't know if you remember a little bit in the last semester, but it's not necessarily. GR of S, what is GR of S? In input of the controller, we have the error. And the output, we have a U. U is the signal which is an input to the system. This means this element here can be written as U of S divided E of S. This means the error is multiplied by this component here, which is represented the P controller. Could you remember the P controller multiply the error? This element here can be seen as a D controller because this element here multiply E, but S, you remember the derivative theorem in Laplace? S states the derivative in Laplace. This means we approximate at the end this more complex controller in terms of PD controller. Why this could be useful sometimes? Yeah, because we can buy a P controller and we can set directly the PD in the sense. Excuse me, PD typically is a PID controller. We set the integral to 0. We set the P to this value with the resistance and so on, and we set the derivative with this coefficient here. Or we realized in discrete form, we have to discretize this controller here. This is another chapter of control systems. Yeah, is PD is an approximation of this. Now, I will show you what changes in case I have to control the velocity. Look, I will show you mathematically. You will see between this element here, or this controller, and this controller is just an integral. The rest does not change. Assuming that S hat 0, this means the same specification in terms of acceleration, term acceleration in this case, to achieve my goal in 1 second, 1 meter per second in 1 second. Of course, the specification must be the same. Now 1 is not, I show you, I hope to have, but it's intuitive. If the specification is 1 meter per second in 1 second, chi I is the same. If the specification is achieve the goal without oscillation in the velocity, S equals 0, I will obtain the same, but in order to obtain the error equals 0, I show you now, I need an integral. I need an integral because I don't have in the loop the integral, which maintain for a goal constant steady state error 0. I will go in depth on this, but please believe me, I'll demonstrate now. Basically, the difference if the specification is exactly the same, otherwise change the values, but not the structure. I mean, the difference is that we have an integral in the velocity. To park the car in terms of control is more difficult, is less difficult than to guarantee the cruise control. Because the cruise control needs structure and integral. I show you this. So we will repeat everything again. Everything starting from the beginning. This really is a standard, again, the difference probably must be now emphasized that this here cannot be, the controller cannot be approximated with a PD controller anymore. What is the approximation of this in European? I mean, here we clarify, no? The unique thing that I can approximate if the frequency is not so high, but in any case, what I can approximate to neglect this, what is why I can apply directly this control. If I have this control, instead of an approximation with an PD, in your opinion, what I have? If I throw away this one, I have an PI controller. I don't know if it's visible. If I multiply this multiplied by 1, I have an integral action. By 1 divided S reflect the integration in time. If I multiply this by this, I can cancel S. I have just a constant. This means a PI controller. Basically, to control an auto in terms of velocity, cruise control, let me say cruise tempomat, is more complex because I need a PI control with respect to control and parking phase, which I need a PD control in terms of approximating control. What we did in Volkswagen, we approximate this with just a constant, but variable. What is this basically, roughly speaking? Is something which change with respect to the frequency. Respect to the frequency means with respect to the time, no? In the steady state, you have a value, in the transit, we have another value. This is not wrong to think. We are cancel also this one, and we realize in the P controller, we change over time. This is not a chapter of a Kalman filter. This means adaptive control. Even though this is adaptive, but is self-adapting. This is a little bit more complicated, but we can throw away this D part. Typically, if we don't have disturbance, this is the best one. Of course, if we have a variable to park in a slope, this could have advantages because it's a complex algorithm. Look what happens in adapt P. Yeah.
Nochmal erklären, warum die C jetzt geteilt durch S ist und nicht multipliziert bei S, wenn es um die Velocity geht und wir vorher die Position als Controller haben.
Ja.
Das ist eine Ableitung, also mal S.
Now I will do all calculations, so will be extremely clear mathematically. This depends of the age. Remember, depends of the value of age. If we have or not, we have an integral. I will do analytically. I hope to have. Otherwise, I can do with the hand. Intuitively, you intend. No? Because mathematically, I will do. It's again the calculation of what is the maximal age which guarantees steady state error zero in case of velocity control and not displacement control. Intuitively, we have two possible explanations. Think, yeah, your criticism is the velocity is the derivative of the position. Intuitively, you think I would like to, waiting for a product of S instead of division. Intuitively, I would like to answer so. Yeah, the question is clear, no? Because intuitively, how I can answer you? I have a possible interpretation in this sense. If it's valid, what you say is true, because the velocity is the derivative of the position. But the controller somehow consider an inversion of this function, of this relation, because here this transfer function is not directly the transfer function which reflects position and velocity. It's something which came before. This means, how possible to explain? The output is a velocity now.
Ich hatte es nur am Anfang so verstanden, dass wir von dem einen Controller sofort auf den anderen schließen können. Aber man muss ja nochmal dann das nachrechnen.
If I calculate, you will be convinced. But I would like to find a possible intuitive.
Aber es ist nicht möglich, wenn wir nur den Positionscontroller haben, sofort ohne weitere Rechnung auf den Velocity Controller zu kommen.
This is possible, again, if the specification is the same. This means 1 meter per second in 1 second. Otherwise, change the values. No? When S hat equals 0. Now the question is, your question is interesting. Why is divided is not multiplication? Yes, this is a structural question. Because you're right, you say, if I have a controller which control the position, let me say, and now I want a controller which control the velocity independently of the value. And I think that the velocity is the derivative of the controller of the position. It seems to be that I have to do the derivative of the controller. Seems to be, but the controller is not the transfer function of the between position and velocity. I try to explain. Yeah, the question is why 1 divided S instead of S. The value is clear that can change if the specification numerically is not exactly the same. It's the same if 1 meter per second in 1 second and S hat 0. This means I don't cross the limit of, yeah. Otherwise, I have a different values. But the key point is why this integration instead of, now I show you the calculation later. Let me intuitively answer. It's a good question, because intuitively I say, if the derivative of the position is the velocity, I have the controller for the position, I multiply by S. I mean, it seems to be intuitive. Let me see if I'm able to intuitively to answer you. I am not sure if I am able. The position we call X. Here we have US. Here we have something like that. Chi I. Let me consider just chi I divided 1 divided S. Now, let me see. This is the key point which we want to analyze. To compare with something which must be calculated, GS1, GS2. Let me write directly exactly the transfer function. So we save time. Yeah? What is this? It doesn't matter what. No? Tau multiply S plus 1 is something which recalls the position. And now, yeah, I can be more precise with our transfer function, but this is Ja, we have a constant and a parameter. I mean, look. Here's the transfer function K1 divided S, which multiply everything tau multiply S plus 1, I can write, no? In which this Ki is 1 divided B. Excuse me, 1 divided B. The velocity is again 1 divided B, our K1, the same constant, tau, which is the same, plus 1, but without S. This means I can write here K. Basically, the transfer function is exactly the same. Did you agree, no? Tama, because change just. I don't have S here. Again, this tau in our case is M divided B, and K in both cases, of course, no? Is 1 divided B. In both cases, yeah. Yeah, exactly. This is the velocity. Now probably we can see intuitive. No? No, excuse me. That's, I don't, that's contrary. No, this is 1, yeah, and this is 1 divided S, right? The velocity, it seems to be, I need. Excuse me, I mixed. Now we can see intuitively why. Because in the, what is this? This is GOL. Did you agree? Must be, in order to, as you told me, to have the same rest of the controller, the same GOL. Let me consider the case 1. And we have, in this case, the same GOL. No? The same GOL guarantee the rest of the controller, G C of S, the same, with the same specification. With the same specification and the same GOL, we have the same GC of S, GC of S. Now we can see that just with 1 divided S, we have the same GOL. It's a little bit abstract, no? I can improve a little bit. Look. No, I would like to leave here. Look at this. Probably you can intuitively write it this form. Here we have the velocity. Here we have the position. Conceptually, it doesn't matter if this 1 divided S is here or in the controller, but must be there in order to have the same GOL. Just with the same GOL and the same specification, we have the same GC of S. We have the same GCOS, which I have to put here. No? Here, I have to put GOS. GOS, you just say, is the same if I start with the same GOL, but I can start with the same GOL. Yeah, the GOL is this multiplied. This is why I have 1 divided S. I don't know if this can help. Huh? Now I show you the calculation. With the calculation, but the calculation, you were right, is a little bit intuitively, it's always something which we have to consider as engineer. It's physically, but this is quite abstract. No? A controller is a quite abstract function. No? It's a function of the error and the output. We have the input of the system. Let me put everything inside, and let me look if I have. I think I have the velocity. No? So we repeat the procedure. Try to do at home, but we will do together also with the tutorial, with different S hat. I will give you in the exam one of both cases, position or velocity control. With the time which we had, we didn't do much more. No? Of course, many considerations. We will see also some other aspects important in general for the applications, this linearization. But this I didn't. One second, because otherwise, if I don't put now in the right form, and then I will scan everything, I lose the math. Let me look for a cruise control. So we repeat the procedure, and analytically we'll answer you why we have one divided S. But I hope that this a little bit can help.
Ja, noch
8 Minuten. I sketch out, and we will do next week. So in any case, next week we have a regular lecture. No? So we can do 2 or 3. The examples are going the same. Once you learn the procedure to read the table basically is because you cannot use the computer. No? Otherwise, this function in MATLAB, if you look in MATLAB, this tool, I don't know, it's the name of tool, both analysis. This function is a parameterized function. Lambda is the parameter over omega t as variable. Then the computer does in 1 microsecond. Within resolution in terms of lambda in accordance with the resolution of the computer. This means it's extremely precise. Nevertheless, we did many approximations. Therefore, this important concept, we look for lambda in the maximum, because this is valid for a large band of frequency, omega tau. This means it's more robust approximation or everything which probably another thing I would like. I have 1 second. Lag. One concept. You don't put a lag, but sometimes we realize, but it's very seldom. If you need to accelerate the system, it's not. We don't do basically so. But if you need to accelerate the system, this means you have to reduce. If you need to accelerate the system, you have to reduce the phase margin. Therefore, at the beginning, I told you the Bode diagram or the Bode method or the Bode theorem states also the measurement of the stability. If you reduce the phase margin, you accelerate the system because the system go towards an unstable situation. When are we on a stable situation? When the denominator, roughly speaking, is close to 0. This means the system starts to oscillate, go faster. And this to accelerate, basically, we used and lag structure. Look here. The lag is minus the lag. This means this Bode phase diagram is minus, as if I subtract or add, it depends on the direction. I reduce the phase margin. The system becomes nervous very fast because it's close to instability. What is the instability, roughly speaking? Very small value of the denominator. This means high value in the back transformation of the system. So reflect this. Divided by 0 or something small, it means something large. I have a very uh, strong answer. Look, we will do next week. Is an exam in the tribe. 1 second. I have how many minutes? 5 minutes? Yeah, 4 minutes to show you what we do. Velocity, force. Exactly what I told you, which I sketched at the end of this lecture. The value is different because I am considering now 10 meters per second as a goal. But look, your question. To reduce to zero steady state error, I have to solve the same problem as before. For what is k? What is k here? For k equals zero, I am looking for the minimum, no? To reduce the number of integers. For k equals zero, look, we have something not zero. Assuming this is 1, I have something not zero, depends on b, but b cannot be 0. It's the friction. This means the p controller, or let me say without integral, is not possible. Consider now k by 1. If I redo the calculation, we will see, because we have an s here, we have an s in the numerator. If I do the calculation, I will obtain 0. This is analytically why we have an integral in the velocity control. The practical reason, Tamo, is we need in the open loop an integral. There is an internal model principle which says I have to have in the open loop structure the part of the transfer function, the Laplace transform of the signal which I have to track. I have to replicate. This is the principle. In the open loop, it doesn't matter if this part came from the system itself or from the computer or from the controller, because this principle, internal model principle, says that I have to replicate in terms of Laplace the Laplace transform of the goal of the reference signal into GOL. This means in the GOL must be present the Laplace transform of the goal. This means if I want to control the acceleration, this means the velocity should follow in a ramp, I need 2 integrator in the controller, because the Laplace transform of a ramp is 1 divided s squared. In the cruise control, I need 1 divided s squared, 2 integral. If I want park, do you remember at the beginning I told you we can switch ramp and then constant? If I want park, I want follow at the beginning the ramp, I need an integral in the place, in the displacement control, in the first part of the displacement control. Because this principle, the principle of the internal model, say I have to replicate in the open loop GOL, I have to be present in the part, we reflect exactly the Laplace transform of the reference. It's a little bit, the principle is called principle, but came from these calculations, Look, basically, we have a 1 divided s, because I would like to follow something like 1 divided s. I have a 1 divided s in the open loop. In the displacement, I don't need, because it is already in the structure of the system. Of course, it isn't a principle, but we can demonstrate mathematically that for the signal. I have to replicate in the open loop the Laplace transform of the goal. Principle of the internal model. Internally should reflect what I want to obtain. Ready? Thank you. Next week we do exercises, and then if I have time, I told you something more in depth on the open problem which I left. Otherwise, we can in the first week of.
Gerne die Sachen alle hochladen.
Yeah. This I do because basically the course is ready structurally then.
Yeah.
And I hope that to clarify this YouTube. I'm almost ready with my YouTube channel. Everything is free, no? If you want to laugh a little bit because my voice is a little bit so, but anyway, I hope that can help. No? Thank you for your attention. We will see next week, same time, no? It's here or per Zoom if you cannot come. Thank you.